He got it on the
Well, hello, everyone.
on the computer.
Just a second. We good?
Yeah.
Okay. Our speaker tonight is Carl Hergenrother. He is the coordinator of the ALPO Comets section. That is, ALPO is the Association of Lunar and Planetary Observers. He's the coordinator of the Comets section of that organization and is currently also the executive director. He has a bachelor's degree in atmospheric sciences from the University of Arizona, but apparently he wanted to look higher than the atmosphere. So rather than becoming a meteorologist, he became an observational astronomer at the University of Arizona, where he primarily studied comets and asteroids. He's a founding member of the Catalina Sky Survey, where he discovered 4 comets and numerous asteroids. Carl spent over a decade as part of NASA's OSIRIS-REx mission to acquire samples from a small near-Earth asteroid called Bennu. His primary achievement there was the discovery that Bennu is routinely ejecting small particles into space. I remember when that was discovered.
Does he know Dolores Hill?
Well, we'll ask him when he gets started. The question is, does he know Dolores Hill? So,
Yeah, of course.
Okay.
I was sitting next to Dolores when I made that discovery.
Wow. So OSIRIS-REx has departed from Bennu. So Carl has moved on to a company called Ascending Node Technologies. What a background. What variety.
Arizona still?
We'll ask him whether that's in Arizona still. It's a small business specializing in spacecraft planning and operation software. What has he not done, you know? Carl has always enjoyed backyard observing. His go-to equipment is a pair of Vixen 30 by 125 binoculars. Since observing Comet Halley back in 1985, Carl has visually observed over 150 different comets. So tonight, Carl is going to be focusing on telling us about the Association of Lunar and Planetary Observers. I'd like to hear about all the stuff he's been doing. Carl, take it away.
Great. Share the screen. Everything looking good? Great. So yeah, thanks for the introduction there. So yeah, I'm down here in Tucson, Arizona. I grew up in actually northern New Jersey, the New York, New Jersey area. Came out to the university to originally study astronomy, but I found that I couldn't, the physics classes weren't holding my interest. My grades were slipping, and before things got too bad, I transferred over to atmospheric sciences, meteorology, because I just found that a little easier math-wise. But I still remained in astronomy and continued observing. Just a little bit before I came out to the university, when I was still in high school, this is probably about 1990-ish, I joined the Association of Lunar and Planetary Observers. I saw an ad for them or a write-up for them in Sky and Telescope, and they were one of a few different amateur professional organizations that I joined around that time. And I kind of drifted away from the ALPO once my career had gotten going, and I basically spent so much time observing professionally that I didn't quite have any time to observe in an amateur capacity. But then when I became part of the OSIRIS-REx mission, that ate up so much of my time that I didn't have time anymore to observe professionally. So to kind of fill that void in my life, I need the night sky, I started observing from my backyard again and started observing more in an amateur way. And so I rejoined the ALPO. This is probably about 2008, 2009. And by about 2013, I'd been designated as the coordinator or the lead for the Comets section. And a few years after that, I was asked to join the board of directors there. And the way we do the board of directors is every 2 years, we kind of rotate through the executive directorship. So you serve a 2-year stint as executive director, and then your next stint may not come up for another 6, 8, 10 years or something like that. So I'm actually in the month 23 of my 24-month term of office as executive director of the ALPO. And so what I would like to talk about is just kind of introduce the Association of Lunar Planetary Observers, its history, what we do, how you can help if you would like to, and then go a lot deeper into just observing comets, because that's kind of my thing. So what is the ALPO or the ALPO? Well, the ALPO last year just celebrated its 75th anniversary. It was formed in 1947 by Walter Haas, who was living in Las Cruces, New Mexico at the time. In fact, I think he lived there for most of his life. 1947 was kind of an interesting time for planetary astronomy. It was right after the war, so all of astronomy took kind of a hit during those war years, especially in Europe and Asia, where a lot of observatories were destroyed. A lot of people, of course, were serving. And planetary astronomy was kind of in a bad place because it never quite recovered from the whole Canals on Mars fiasco. So it was kind of looked down upon in these early 1940s. And also the problem is you had all these big, large telescopes being built. You had the 60-inch and the 100-inch on Mount Wilson. 1947 is right around the time that the 5-meter, Mount Palomar 5-meter was built. And everyone was starting to do astrophotography. Everyone was interested now in how large and expansive the universe was. They were doing observations of high redshift objects. We had just discovered that galaxies really were, kind of separate Milky Way type objects, not just nebula in our own galaxy. And so cosmology was really at the forefront in astrophysics, and planetary science had kind of been there, done that. We know everything there is to know about the planets. So the ALPO was kind of formed as a way to get people who were interested in planetary astronomy to talk to each other and to really figure out, keep these objects under constant observation just to see how they really are changing. One of the interesting things is back then we still weren't 100% sure there wasn't an atmosphere on the moon. So one of the early ALPO observational programs was to actually look for meteors that might be burning up in the atmosphere of the moon if it had an atmosphere. And a lot of the people who would eventually become major players in the professional planetary science field, really in the 1960s and onward, once we decided to go to the moon, actually got their start as high school kids or as undergraduates with the ALPO. So the ALPO is kind of structured very similarly to the British Astronomical Association. It's got 18 different sections. And you see here, basically each major planetary body, whether it's the sun, all the planets have their own section. We do kind of merge Uranus, Neptune, and Pluto and any of the Kuiper Belt objects into the remote planet section. We've got sections for comets, for meteors, even for meteorites. We just started a new one for observing exoplanets. Not quite objects in our own solar system, but why limit yourself to the 8 or however we define planets now in our solar system, 56, when there are thousands and thousands and hundreds being discovered every year that are actually orbiting other planets. And then we have sections that aren't really related to observation per se, but are outreach, training. People can join the ALPO and learn how to observe these objects, how to do your imaging, how to do drawings. And we do have a nice, vibrant publication section and online section, which I will get to in a little bit. So just kind of deeper dive here on one of the sections. This is the lunar section, which, yes, means you're observing the moon. But within that section, there are a lot of what we call observing programs. For example, there's the lunar transient phenomenon. People do see things on the moon. They do see things change in, time scale of seconds to minutes, sometimes on the moon. And these have been seen basically, you can even go back to the Canterbury monks in the 1100s. He looked like they maybe saw a potential impact of something on the moon. And while a lot of these lunar transient phenomenon are probably something nearby, it's probably an atmospheric phenomenon or even, thermal currents within your telescope, we do know that the moon shows signs of still being volcanically active, at least in the last couple million years. So the moon is not necessarily a dead body. Lunar meteoritic impact search. Here's an example of changes actually occurring on the moon that we have now seen happen hundreds of times, where basically meteoroids come in, impact the moon, and create a flash. And those flashes are definitely detectable with video array cameras. I'm going back to my introduction when I discovered those particles being thrown off the surface of asteroid Bennu. And asteroid Bennu was assumed to be a dead body, about half-kilometer asteroid. It looks like every day particles are being flicked off, and these are particles on the order of like millimeter, centimeter size, kind of like almost like cornflake sized and shaped. And what we're thinking is these particles are just laying on the surface, and a micrometeoroid impact comes in, hits the surface, and ejects this stuff off. So it's another example of meteoroid impacts hitting airless bodies and creating phenomena that you can study. And a lot of the other programs deal with various other geological formations on the moon, like various craters, lunar domes, which are actually volcanic swelling due to volcanic activity, and other things. And a lot of these programs publish in the Lunar Observer, which is a nice monthly publication that's put out by the Lunar Section. It runs roughly almost about 100 pages. And then some of the stuff is also published in our quarterly journal, which is called the Journal of the ALPO, or the Strolling Astronomer. So do you have to be an observer? Do you have to observe for the ALPO to become a member? And the answer, of course, is no, you certainly don't. In fact, most members don't contribute observations at all. You could also flip that question. Do you have to be a member of the ALPO to contribute your observations to the ALPO? And again, the answer is no. You don't. Of course, we would love for you to be a member, help support the organization, but probably about half or maybe even more of the observations that come into the ALPO are by non-members. But there are some real nice benefits of being a member of the ALPO. For one thing, we do have this nice quarterly journal, and as one amateur nicely put it, the Journal of the ALPO is where sky and telescope and astronomy leave off. We have another events that anybody can join, that anybody can participate in. You don't necessarily have to be a member of the ALPO. We do have an annual conference. Our next conference is coming up at the end of July. It'll be Friday and Saturday, July 28th and 29th. And though you do have to be a member of the ALPO to present, if you just want to listen in, whether through a Zoom link or you can actually go to our YouTube channel, you can watch the event. Even though it's 2 days, it's about 4 hours per day. We try not to make it, a 12-hour-a-day grog like some conferences can be. And that'll be in about a month and a few weeks from now. And we have other free online content. Tim Robertson who's the kind of the head of our online section, is producing these rather routinely producing podcasts. We call them the Observer's Notebook. And these can run anywhere from 10, 20 minutes up to an hour. And I've done quite a few of them, just discussing either bright comets in the sky, or I try to do one every year where I just talk about the comets for the upcoming year. He's actually started a nice series of talks about various historic observatories around the world. As you can see, he's got one on Lick Observatory and the Vatican Observatory. And I think he started it with the Griffith Observatory. We have nice discussions on upcoming meteor showers, and usually for various planetary apparitions. You can access these podcasts either at YouTube or our YouTube channel, which is just Association of Lunar Planetary Observers, and also on our SoundCloud platform that we have. But if you do want to become a member of the ALPO, here's some of the perks that you would get as a member. As I mentioned before, we have the Journal of the Association of Lunar and Planetary Observers, the Strolling Astronomer. It used to be more known as the Strolling Astronomer back in the olden days, but now it's more of the JALPO, the Journal of the ALPO. This comes out quarterly, and again runs about 100, maybe 120 pages. And in there, you'll have various section news where we talk. Each of the sections will kind of give updates on what had been observed over the previous quarter, as well as things to look forward to in the upcoming quarter. And we have what we call apparition reports, where every year or so, basically from solar conjunction to solar conjunction, we talk about what was observed on that planet or comet in that case. For example, here's one, not so much an apparition report of a single apparition, but a report of all the apparitions observed for Mercury, which of course is one of the most difficult planets to observe because it's very close to the sun. But these were observations made during 2018. So a lot of the work that you do submit does get published, at least gets referenced. You'll get a mention, and some of your images will even get published in the journal. Each of the sections sometimes will also have their own kind of online publications. I mentioned already the Lunar Observer, which is the publication of the lunar section and runs about 100 pages. There's the Minor Planet Bulletin, which has almost taken on a life of its own, almost like it's grown. It's expanded much even beyond the ALPO sphere of influence in a way. And this is kind of the go-to publication for anyone who's studying asteroids or doing light curves. And this, again, is a publication that can run 100 pages or so. It's quarterly. And even professionals will publish observations in this journal of their various observations of asteroids, how fast they're rotating, their colors, phase functions, and other exciting things asteroid-related. And then I try to publish a monthly publication for basically just comet news, where I just talk about what comets are observable in the upcoming month, a little bit about the observations that were made in the previous month, and just kind of make predictions as to how bright these comets will be and where in the sky they'll be. And of course, a lot of this can also be found on our website. A really important part of our website is what we call our image gallery, where each section has their own section, where we basically, all images that are submitted to the ALPO get put online. And you can see different sections for different kind of tabs you can click on for each of the major observing sections. You can also find, even though the ALPO isn't available, the journal of the ALPO isn't available immediately for non-members, after a year or two, all the older ones are available, and you can actually go back to the original stuff published in 1947 and look through the old journals as well. Just to kind of show you what the comet one looks like. So right now I've got about 7,000 images of over 500 comets in the comet section image gallery there. With comets going back to really when the comet section formed, which was 1956, 1957. The comet section had formed really in direct response to the, we had two really good, bright, great comets in 56 and 57. I think it was both in 57, Aaron-Roland and Mercash. And then this just kind of shows some of the images that are there for one of the, not this most recent Mars apparition, but the one before that in 2020. So a question I always get is this real science? Is this even worth observing these objects for the most part? Or is it just for fun? And of course, if you're observing planetary stuff just for fun, that's great. I observe plenty of stuff just for fun. Not every observation I make has to have, scientific value. But a lot of the observations can have scientific value. In fact, the amateur astronomy community is often kind of the astronomical community's early warning system. Quite often it's amateur astronomers who are the first one to detect, the start of a new dust storm on Mars or various storm outbreaks on Jupiter or Saturn. In fact, a couple of years ago, there were observations made of Venus that really suggested that we may have caught a volcanic eruption in process. There was actually a bit of a bulge where the atmosphere seemed to bulge out on the limb of Venus. And one of the serious explanations for that was maybe there was a volcanic eruption, and that was just pushing up the atmosphere. It's mostly amateurs that detect meteoroid asteroid strikes on the moon and Jupiter as well. And of course, meteor storms here on Earth. And again, being comet related, almost every comet outburst or comet splitting event or rare morphology is being found by amateurs first. And then it's professionals who basically get the bigger telescopes and look at things. And of course, amateurs are at the forefront of many of the long timescale studies, not just in planetary astronomy, but variable star studies, asteroid light curves, comet brightness, and such. And I even found for my OSIRIS-REx work, we were supposed to calibrate our imager by looking at standard stars, and we couldn't do it for a reason. We ended up being undersampled, so we couldn't. And if anyone's tried to do photometry with undersampled images, kind of can't. So I had to look for extended sources to do photometry on, which basically meant I had to look at the planets, mainly Jupiter. And the only people who had studied actual photometric studies of how bright Jupiter has been over the last few decades were amateur astronomers, including some stuff that was published in the ALPO. So a lot of this work does come in very handy. And just to kind of make my little sales pitch, how to join, the easiest thing is just go to our website. which is www.alpo-astronomy.org. I kind of wish I'd put the URL of the website on here, but forgot to do that. And we're not expensive. We're pretty affordable. If you just want the digital journal, it's about $22 a year. If you want the paper journal, which I do get, about $55 a year. But now on to observing comets. So that leaves the overview of the ALPO, and now I'm going to talk a little more on how you can observe comets and do it with your basic backyard instrumentation. So what are comets? We've got planets, of course, which are major bodies. Spherical, most cases differentiated, which means they're massive enough that they actually had internal heat. And basically the light stuff floated to the surface, what we call the crust. The heavy stuff sunk to the middle, what we call a core. And of course, some of the planets are very rocky, while other planets are very gassy, like Jupiter and Saturn. And some are kind of a mix of rock, ice, and gas, like Uranus and Neptune. And then we have all this leftover material from when the solar system formed. And of course, asteroids are usually assumed to be dry or have a minimum amount of volatiles or ice, though we're finding that's not always the case. But comets in general are really just small, icy bodies that are experiencing mass loss. Basically, objects that are, even though we have detected comets that are on the order of 100 kilometers across, most of them are already, kilometer or so, many even smaller. And really what differentiates a comet from an asteroid usually and practically is whether or not you see activity, whether the comet looks fuzzy, which of course is where kind of the name comet comes from. It's actually Greek for long-haired or hairy star, rather than asteroid, which comes from the root for just a star-like object. Most of these objects formed in the outer solar system, probably well beyond the waterline, usually beyond Jupiter. Many of them are still out there in the outer solar system in the Kuiper Belt object, though some have been kicked even further out into the Oort cloud. And just there on the right, just to show a few examples of orbits, we have short period comets, which are objects that orbit on the order of, the shortest one is every 3 1/3 years. That's Comet Encke, which will be coming back in a few months, up to maybe 20 to 50 year orbits. You've got the intermediate period comets, which are kind of the Halley family comets, which go from 50 to a couple 100-year periods. And then you got the long period comets, which can go from that up to millions of years. And in some cases, due to planetary perturbations, they may be a one and done event where they come around, the gravity of Jupiter and Saturn perturbs their orbits enough that it kicks them out and they end up on a hyperbolic trajectory and leave the solar system forever. And a fourth category that probably didn't exist when this schematic was actually drawn up are the interstellar comets, of which we had one interstellar asteroid and one interstellar comet. And these are objects that were ejected from another solar system, probably spent millions or tens of millions of years floating through interstellar space, and then just happened to make a close approach with the sun and came through our solar system. Just talk a little bit about basic comet observations. Now, the nice thing about observing comets is the same thing that can be said for variable star observations or for observing planets, is that you don't need any real specialized equipment. Doing, your basic comet observations, especially if you're, determining how bright a comet is, you just need your eyes, and depending how bright the comet is, binoculars, a telescope. If the comet's bright enough, eyes alone may actually do it. And so your basic comet observation really consists of just a little bit about the observation itself, who you are, when you observed, where you're observing from, what equipment you used. A little bit about sky conditions can always help. And then you can either just provide a textual description of a comet's appearance, the size, shape of the coma, how condensed is the coma. Comets can range anywhere from almost star-like when they're really close to the sun, or just had a most recent outburst, to very, very diffuse, where it's almost hard to see that there's any real structure within that coma. It's just kind of a amorphous buzz on the sky. Whether the comet shows any tails, and if so, how long and what direction. It's a really nice bright comet. Sometimes you can tell that the tail is curved. And does the comet show any color? Earlier this year, there was a lot of news about the nice bright green comet. And yes, all comets that get within about 1.5, 2 AU of the sun look green in imaging, but through the telescope, And as mentioned before, I've observed about 150 comets visually. I can count probably on one hand the number of those comets that actually showed real color other than your usual kind of very light grayish that you see when you look through a telescope. Sometimes comets can look very, very green. They're very gassy. And in the case of Comet Neowise a few years ago, when it was really close to the sun, it was very, had produced a lot of dust. And same goes for Hale-Bopp, which was very dust rich. It looked very, very yellow. Of course, a drawing or an image of the comet also helps a lot. And one thing I use a lot is trying to determine how a comet changes brightness with time. So an estimate of the brightness can be done. And you can do that pretty much the same way, again, that you do variable star observations, where you compare the brightness of a comet with a star that's in the field or a standard star that's nearby. The tough thing here, of course, being that comets are big diffuse objects. And so you actually have to compare a out of focus star with the in focus comet. Just to highlight some, and by the way, if there's any questions, don't feel shy to break in and ask me. I'm okay with questions on the spot. Just show a few other of the images and sketches, and really want to look at the images that are over in the lower right. So the image that's kind of nice color, it's got a little bit of green and stuff like that. That was an image of comet 46P Vertinen, which was observed. This observation was from Italy, and that's a CCD observation. Within about 20, 30 minutes of that observation, Michael de Koninck in France observed the same comet visually. And I think he was using an 8-inch at this time. And he actually sketched out 3 jets. And he had one jet that was going about, 9 o'clock there, another jet that was going about 10:30, 11 o'clock, and then another one at about 1 or 2. And those actually correspond with the jets that were imaged in the CCD image. So it shows you that even just visual observing through, say, 8-inch telescopes or even smaller, quite often you will see many of the same near nucleus features that you would that are otherwise being imaged. So it's kind of a nice proof there that visual observations will detect a lot, similar to what CCD observations detect. As I mentioned before, photometry of comets can be tricky. In addition to doing photometry using visual methods, you can also do CCD stuff. Here, usually what we try to do is we try to measure the entire coma to get because when you're doing your visual observations, you're comparing the in-focus comet with an out-of-focus star, but you're getting basically the magnitude of the entire coma or the head of the comet. For CCD observations, it used to be for a long time, people thought that all photographic and CCD observations were always 3-4 magnitudes fainter than visual observations. And for a while, people thought that that was just something that was actually inherent to how the observations were made. And there's a little bit of truth to that. Usually what happens is, this is Comet Leonard from about 2 years ago, and this was just taken with a 72 millimeter refractor, which if you can see my videos, the one sitting right here. And depending on how you kind of stretch or scale your image, if you want to, have a dark background, which is how a lot of us look at astronomical images, it looks like the coma is pretty small. Even if you do a log scale where, you can see a little more detail within the nucleus, but still you're seeing a pretty small pretty small coma. But if you really stretch the contrast, you notice that the coma is much, much bigger. And one thing I do usually to determine how large the coma is on a comet is I use DS9, which is a bits observing tool, which is freely available. And so you actually can plot up isophotes. And so with that, you can measure exactly how large you should measure to measure all of the flux that's coming from the coma or head of a comet. And notice how here, even with the log scale stretch, I would have just, visually picked a much smaller aperture. And then, of course, if I were using just my regular linear stretch here with a dark background, it would have been much smaller. So in this case, I would have ended up with a much fainter magnitude than I would when I measure it out here. And so what I do is I collect observations from all the various contributors who submit their observations to the ALPO, and it's a mixture of visual observation as well as CCD or CMOS, digital observations. And even after, doing the observations, you still find that quite often there's still a bit of noise. So I will take everyone's observations, I will plot them up, and I'll kind of just look for general trends. Like, are some observers consistently bright, or some observers consistently fainter? And then I'll just scale things and try to line them up. And so I kind of create what they call a personal bias correction, and do that for all the comets. And usually you end up with a pretty reasonable light curve. In this case, this is a short period comet, 64P Swift-Garrels, comes around roughly every 8 or 9 years. And back at the end of 2018, 2019, got up to about 8th magnitude. And you can see where it quickly brightened from pretty faint, peaked around 8th or 9th magnitude, and then faded again, as most comets do over the course of a few months.
I plugged it in over here.
You turn on, you didn't turn on.
Oh, is that a question?
I haven't turned on.
You gotta turn the TV on. Oh, what are you trying to watch it on here?
Yeah.
Oh.
Oh, okay, I'll continue. Another thing you can observe is coma and tail morphology. In the image on the left, that's Comet Neowise from 2-3 years ago. And these are images taken with a 17-inch telescope. And it does show these kind of corkscrew, almost like your lawn sprinkler, as it's spinning around, would create these corkscrew jets that go around. And that's exactly what the comet is doing. As the comet nucleus is rotating on the order of, I think it was about 7 or 8 hours for each rotation, you've got an active area that's spewing out dust and gas, and kind of like a lawn sprinkler, as it's rotating, it's sending out these jets. And those are observations that were first made, mind you, a 17-inch telescope. You would have seen this in a smaller telescope, but it was amateurs who first came up with detecting this corkscrew type feature and measuring the rotation rate of the nucleus of the comet. The image over here on the right is, again, a short period comet, 67P Churyumov-Gerasimenko. If that name sounds somewhat familiar, that was the target of the European Rosetta spacecraft mission that went into orbit around the asteroid, around the comet. And that's the comet up close there. Kind of has that weird shape that looks almost like a rubber duck. And the spacecraft was in orbit around the comet for about a year or two, and then actually had one probe that landed on it, and eventually they landed the main spacecraft on the surface as well. What's cool about this shape, which does seem to be fairly common for comets, is that probably at some point, hopefully soon within our lifetimes, maybe it'll take a little longer, this comet will probably split in two. And when that happens, 67P will get much brighter, at least for a short period of time, and then may even result in 2 separate comets, and maybe even a multitude of other smaller comets traveling along the orbit of the original comet there. This image here was taken by Dan Bartlett when the comet was near its brightest back at the end of 2021. What's cool here, and this was just taken with a RedCat 51, so you're talking a 51 millimeter refractor, though it did use a lot of exposures. That's about 210 minutes worth of exposures here. But what you'll see, you've got kind of the green, blue-green here is the gas coma, and that's near the head of the comet. You've got a dust tail, which is dust that's been released over just this last apparition that occurred. And then if you look closely, there's a line that kind of goes through the comet's head and out the other side. And that's actually a dust trail, and that is heavier dust that was released over many returns and orbits of the comet. What you're looking at there is basically the comet producing a meteor shower. If the Earth were, in this case, the Earth doesn't go through this comet's particular meteor stream, but of course we go through meteor streams like Swift-Tuttle for the Perseids, Phaethon, which is a mostly inactive body for the Geminids, Halley's meteor stream for the Eta Aquarids and the Orionids. But if we were to cut through this comet's orbit, you would actually get a meteor shower. So it's these heavy particles that are kind of lining the path of the comet that would create a meteor shower. And again, this is all stuff that can be done with, not going to say everyone's ground-based backyard stuff, but you don't need a lot of stuff to do this, though it may sometimes take a lot of observing time to get down this faint. And just a few more examples. I like to point out the comet here. This was a C2019 Y4 Atlas. This was a comet that was in the news for a little bit, early 2020. It was predicted to be a comet of the decade or whatever, and it was supposed to get up to about zeroth magnitude to first magnitude, and got up to about 7 and then stopped brightening. And what happened was the comet actually fell apart. And if you look very closely, you'll see that the coma region actually breaks up into a few components here. So the comet had actually fallen apart. What's really interesting about this is, of course, we all remember the spring of 2020. That was the COVID lockdown time. Almost every professional observatory was shut down. So basically the only real record of this comet's breakup occurred because amateurs were observing. And of course, with everything locked down, they had even more time to observe because a lot of us didn't even have to go to work. So we still had to work, but at least you had to work from home. And the only actual professional observatory that was still functioning was Hubble. So Hubble did get some observations of this comet. But this was a great example of how amateur work really filled the gap when the professionals were all shut down because of COVID. And one thing that we don't have many observations of, but I would love to see more observations of at the ALPO, is comet spectroscopy. The image here on the left is, again, it's comet Neowise back when it's at its brightest. And this was just using what they call the star analyzer, which is basically just a small, low resolution prism that you can, it's in there 1 1/4 filter holder. So you can stick it in your filter wheel or even screw it onto your eyepiece if you want to do visual observations. And here you got an observation of a Neowise, and you've actually got the spectrum of Neowise. The most important thing here is that you do see some of the gas bands, a little bit here in the blue. We call them the swan bands, a little bit in the green, another one in the green. And this must have been an observation taken probably about 3 weeks after perihelion. But you'll notice here, there's a little bit of yellow, and that's actually ionized sodium, what they call the sodium D line. Had this particular spectrum been taken, say, 2 weeks earlier, this yellow line probably would have been the brightest feature in the spectrum because once you get within about half an AU of the sun, the sodium really takes off, really gets ionized, and comets look very, very yellow when they're close to the sun. And here's a more high resolution spectrum taken of the same comet. And here again, you can see that sodium D line showing just how yellow it is. At least the dust is yellow. And then the various swan bands, which are these diatomic carbon features here. And then which all these kind of give cometary heads those kind of a bluish green glow that's so common in astrophotos. And actually, if you did have observations that have this high enough resolution, you could actually measure the production rate, how active the comet is producing sodium, how active it's producing cyanogen, how active it's producing. In some cases, you get not just a measure of these daughter products, because basically we're seeing molecules that have been broken up by the sun's ultraviolet radiation, but you can also go back and figure out what the production rates were of the parent products, which in a lot of cases is water and ammonia and methane and other sort of things. So I mentioned and showed a lot about this comet Neowise. And while I wouldn't call it a great comet, it really was the really good comet of 2020. And it was the last really bright comet we've had here in the Northern Hemisphere. And really the last really good bright comet we've had in the Northern Hemisphere since Hale-Bopp in 1997. There was Comet McNaught, which was really good, but that was in 2007. But that was much more of a Southern Hemisphere object. Though you could have seen it during the day here from the Northern Hemisphere. And then for some, you could even see a wisp of a tail breaking above the horizon. And then there was another great comet, Comet Lovejoy, which was a Croix sungrazer a couple years after that. That also was a Southern Hemisphere only comet. But Neowise was a nice comet, got up to about magnitude 1, 1.5 in early July 2020. As it pulled away from the sun, and by the middle of July, it was nicely observable. Here's a great picture taken of the comet sitting over St. Peter's there in Rome. And this is probably one of the funnest kind of observations, and one I was able to watch visually, of just because usually as comets are rising, of course, the tail is pointing away from the sun. So the comets usually rise tail first. If we're in the evening, it would be setting head first. But in this case, it was rising in the morning sky. And before the comet rises, you start to notice the tail almost like a searchlight beam coming up from the horizon. So it was kind of fun to watch that in real time, and then eventually the head comes out. Neowise ended up producing two quite significant tails. The images there on the right, especially the one in the upper right, shows a 30-degree gas or ion tail and a 10-degree but heavily curved dust tail. And in fact, if you look really closely, you can actually see the Big Dipper here, just to kind of give it a little bit of scale and perspective. And that again was taken with a pretty, basically that was just a telephoto lens, imaged for a couple minutes. Of course, for most of us, that's not what the comet looked like. As great as, you know, Comet Neowise looked, for most of us visually, or even through small binoculars or even large binoculars, the comet looked like more like what you're seeing in these pictures here. And that's fine. And that's another question I always get. And in fact, I'll have to admit, I suffer from this as well. Even though I submit my observations of comets to the ALPO, I'm not a very skilled planetary imager or planetary observer of the planets. So I always feel like my observations just aren't worth submitting. And I get that question from a lot of people who even produce really awesome images. And it's like, would you be willing to submit them? And they're like, oh, my images aren't very good. But the fact is, all observations are worthy of submission. Yes, it would, you know, trying to go backwards here. Not every observation can look like this. Not every observation can look like that. Not every comet produces that sort of appearance. But really, this is what the comet really looked like to the average person. If you're going to compare observations of comets made 500 years ago when there weren't telescopes, there definitely wasn't any imaging capability, you're going to have to compare them to what the observations looked like to your eye. And so I don't want people to feel like they have to compete with the best people who have the most experience or the most expensive setup. All observations are important. It's possible your observation may be the only one taken at a particular time. So you may be the only person to witness a particular event. This is especially true when you're looking at the planets or looking at the moon and you catch a meteoroid impact on the moon or Jupiter. It's an event that occurs on the order of a second, maybe even sub-second, maybe even just a couple seconds. And so how many people are actually looking through the eyepiece at that time? So all observations are important. And you'll be amazed at how much you can see even visually, looking at a comet's head, looking for various jets like I showed on the previous slide, or various structure in the tail. A lot of that stuff is there to be seen. And sometimes a lot of that, it's easier to see that because our eyes are actually a better detector with a better contrast range than CCDs can. So a lot of what I showed was comets that have already showed up, that already came and went. But what about comets that are up and coming? At any one time, it seems like there's always at least one or two comets in the sky that are brighter than about 10th magnitude. Every year, there's at least one or two comets that get up to maybe 6th or 7th or 8th magnitude. If we're lucky, we'll get a, you know, borderline naked eye comet maybe every 3-4 years. And then every 20 years or so, we'll get a great comet. Right now, there's actually two comets that are visible in the northern sky. There's C2020 V2 ZTF and Z2023 E1 Atlas, which I actually saw just last night with my binoculars. Not the brightest comets, about 9/10 magnitude, but in the circumpolar northern sky. We have another comet coming in that will be brightest next month called 2021 T4 Lemon that could get up to 7th magnitude. Unfortunately, this comet is going to be more of a southern hemisphere object when it's at its brightest. And I should have explained that first. Of course, you got the comets listed here on the left. You got the dates at the top. The number is actually how bright the comet is on that date. And the objects that are kind of bolded here with this bolded box, that means they're observable from the northern hemisphere. So for example, 20 V2 ZTF and 23 E1 Atlas are both northern hemisphere objects, while 21 T4 Lemon starts off as a northern hemisphere object. It's really more of a southern hemisphere object. Maybe here in Arizona, I might be able to keep it in a contact observation for the entire time, but probably up in your neck of the woods, you might lose it for a couple weeks. And then it comes back out again, back in the northern hemisphere. 103P Hartley, which was an object I actually showed a few slides back. I'll actually go back real quick to show you. There it is. Whoops. This is the object here. It was observed by the NASA Epoxy mission, which flew past it back in 2010. And so again, just like a 67P, it actually looks like it's two pieces that are kind of starting either glued together or falling apart. So it's very possible this comet will be split at some time in the future. hopefully soon, because it's always fun to watch comets break up because they get extremely bright. And they usually survive to keep going after that. But 3P Hartley will be coming around towards the end of this summer into the fall and get up to about 7th magnitude. We have 2P Encke. The 2 means it's the second comet to have been recognized to come back. The first comet, of course, being Comet Halley. Encke is kind of our frequent flyer of the inner solar system. It orbits the sun once every 3 1/3 years, which does make you wonder where Comet Encke actually comes from originally. Most comets, especially short period comets, come from the Kuiper Belt, which means, the gravity of Uranus and Neptune kind of bring them in, and then over time they kind of play hopscotch with the other planets down to Jupiter, and then they get kicked into the inner solar system. But usually they have orbital periods on the order of 5 to 10 years. Encke is much shorter at 3 years. It does suggest that Encke may have originally originated within the asteroid main belt. So either this is a very volatile, ice-rich, carbonaceous asteroid that got kicked onto a near-Earth orbit and is now acting like a comet, maybe just in, for about 10,000 years or so until it runs out of volatiles. But it's an interesting object. It unfortunately was going to be the target of a NASA mission called Contour, but that mission blew up leaving Earth orbit. So we never did get a chance to fly a spacecraft past Encke. But Encke will be coming back, as it does every 3 1/3 years, in August, and could get up to about 5th, 6th magnitude, though it'll be pretty close to the sun. And then next year, we do have a bunch of other comets that will also get bright, but I would like to concentrate on 3 in particular. 12P Pons Brooks, 13P Obers, and 2023 A3 Tucson, which I may not be pronouncing correctly, Tucson Atlas. So 12P Pons Brooks, and this is the same thing for 13P Obers, are Halley family comets. And Halley family doesn't mean they're genetically related to Comet Halley, but that does mean they're on a similar orbit with similar properties as Halley. In this case, they're orbits that go from close to the sun out to about Neptune's orbit or so. So, Halley comes around every 75, 76 years. In fact, this year does mark the aphelion. So we're halfway. So the point at which Comet Halley gets furthest from the sun, that occurs on December of this year. So Halley is now directly in between its 1986 apparition and its 2061 apparition. So we're halfway to the next Halley return. But for Pons Brooks, it comes back roughly every 71 years. This was discovered by John Louis Pons in 1812. Pons does hold the record for the largest number of visual comet discoveries. And in fact, he just got another one a month ago. He had discovered the comet back in the early 1800s, but no follow-up observations were reported at the time, at least not in a timely fashion. Observations were eventually published many decades later, but no one really made the connection. And a group that's working on a new book on unconfirmed comets was able to link up Pons's observations with other observations made. And so Pons actually now has credit for yet another discovery. And that was done almost 220 years after the discovery of the original object. But Pons Brooks was discovered in 1812. It was rediscovered by William Brooks, I believe in upstate New York, in 1884. And then it was reobserved again in 1984. It does look like this comet was observed back in 1386 and 1457, and possibly back in 245 AD, but that's a little bit of a tenuous linkage. It comes to perihelion in April of next year at 0.78 AU. The object is very outburst prone, which means every once in a while it'll have an outburst of activity which will increase its brightness by a few magnitudes. So that's always fun to watch for comets. And as you can see on these images, drawings made of Pons Brooks, and this was made back in 1884, you can see it does show jet structure, just like Neowise showed. So it could be an interesting object for imaging or for just kind of high magnification image, visual observing of the comet's head. And this is an object that should reach about 4th magnitude in March and April of 2024 as it's diving towards the sun, and will be a northern hemisphere object until it gets to about perihelion, and then it shifts to being a southern hemisphere object, but could be a nice 4th magnitude object. Not the best return, but not bad. And then there's Comet 13P Obers. This was discovered actually only 3 years after 12P Pons Brooks. Has a very similar rotation period. This one's 69 years versus 71 years. So these two always seem to be coming to perihelion a few years apart, and now it just so happens they're coming to perihelion in the same year. Like I said, discovered 1815, reobserved in 1887 and 1956. Perihelion will be on June 30th, a little further from the sun than Pons Brooks, but it'll be at 1.18 AU, and should reach about 7th magnitude. And this object will be observable and brighter than 10th magnitude and observable from the northern hemisphere for a good chunk of the middle of the year, basically the entire summer from late April through mid-September. And so what about the third comet, which is already being heralded as potentially the next great comet? And you can already see, newly discovered comet arriving in 2024 could be brighter than Venus. And this, of course, is C2023 A3 Chutchan Atlas. So this comet was discovered at 19th magnitude back in January of this year at Chutchan Observatory. Now you can translate it, that was in China. You can translate that as Purple Mountain Observatory. And Chutchan is kind of the anglicized version of that name for Purple Mountain Observatory, which is what the IAU traditionally uses. There are actually other comets discovered by that observatory. And in fact, there's another one. You go back here, 62P, which is a short period comet, which will get up to 9th magnitude towards the end of this year, which was observed by that same observatory, but that was back in the 1950s, 1960s. So it was first discovered in China in January, and for whatever reason, it just wasn't followed up. And then it was rediscovered by the ATLAS program, and ATLAS is a near-Earth asteroid survey that has telescopes in Hawaii, and now they have telescopes in Chile as well as South Africa, and they're covering the whole sky, a bunch of really fast half-meter Schmidt telescopes, really looking for objects that are on their way in and about to hit the Earth. They're only a few days out, but they're really, really efficient at discovering comets. And so they co-discovered this comet, and hence that's why it has the name Chutchan Atlas. But I'll just call it A3 from here on out. It comes to perihelion in September of next year at 0.39 AU. Right now, it's still a distant object. And in fact, the image here on the right is one I just took with the Sky Gems Observatory. That's a remote observatory with telescopes in Namibia, as well as, I believe, up in Spain and a few other places. And there is the image, and there's 3 nice NGC galaxies there in the image as well. And the comet right now is about magnitude 17. I measured it at 16.9. 16.9, and it's a little hard to see, but it has a little bit of a tail. And so it's still going to be a faint object and really imaging only for this year. Next time it goes through opposition will be April of next year, when it'll still be pretty far out, almost 3 AU from the sun, but could actually be as bright as 12th magnitude. We'll be able to follow it till July, and then we kind of lose it at around magnitude 10, though in the southern hemisphere, they'll be able to follow it a little longer. So the nice thing about this, there's good news and bad news about this comet. And like I mentioned before, people are already predicting that this could be the next great comet. Of course, for every prediction of a great comet, well, there's probably about 6 or 7 predictions of great comets for every great comet that actually happens. But I'll just spell out the good news and the bad news. The good news, A3 will get close to the sun. You definitely want your comets to get close to the sun in order to get bright. So perihelion's on September 27th of 2024, 0.39 AU. This comet gets pretty close to the Earth. Closest approach about 2 weeks after perihelion, when it comes within 0.47 AU of the Earth. It passes through an extremely large phase angle. Now, the phase angle is the Sun-Comet observer angle. Okay, so it's almost directly in line between the Earth and the sun. And why this is important is that when you're at high phase angles, what you end up having is the dust in the coma and tail of the comet preferentially scatters light forward. So you get a boost in the comet's brightness. If you still remember the times of having overhead projectors, or even just looking at a beam of sunlight shining through a window, you'll notice that depending on what angle you're looking at relative to that beam, depending on that angle, tells you how much dust you see within the beam. If you're looking kind of at a 90-degree angle, looking perpendicular to the beam, you don't see a lot of dust. But if you start looking up almost in the direction of where the beam's coming from, you see a whole bunch of dust that's floating through the beam. And that's the exact same principle going on. So comets that end up passing pretty close to exactly between the Earth and the sun end up having this boost in brightness, which can be a boost of almost as much as 6 magnitudes. And in fact, many of the best comets in history have become extremely bright because of this boost in brightness due to forward scattering by dust. Think of the last great comet, which was the McNaught comet, which was 2007, but was only observable from the southern hemisphere. Think of Comet West back in the late 1970s. That's another example. Halley, well, not unfortunately 1987, which was a bummer for all of us who observed it, but most apparitions of Halley, it goes through this high phase angle, which bumps up its brightness by about 1 or 2 magnitudes and helps the fact that Halley is already an intrinsically bright comet that gets close to the sun and get close to the Earth, but you add that on top of it, and it really makes Halley, kind of helps explain why Halley is the most important comet in history and the most observable comet in history. But now the bad news. When the comet's at its brightest, and that's true of all these comets that are, at these high phase angles, that usually also means they're very close to the sun, which means you're observing either in daylight or in very bright twilight. And so unless A3 is already a bright object, it's got to be at least 3rd magnitude or stuff, and then has, 4, 5, 6 magnitudes of enhanced brightness to be like -3, you're probably not going to see it when it's that close to the sun. In fact, I think it's only 3 degrees from the sun when this is at its extreme large phase angle there. Even though it may be too faint to be seen from the ground, luckily we have spacecraft that are always looking at the sun, so SOHO and stereo, so they will have a great view. But probably the most important disclaimer, and the thing that makes me a little nervous about declaring this comet as the next great comet, is that it's what we call a dynamically new long period comet. What that means is that it looks like A3 is making its first approach to the sun. Now, what we do with comets is as they're orbiting the sun, we determine its orbit. And then what they do is they integrate the comet back till it's about 200 AU from the sun before it's gotten close to any of the planets. And then they go, what did its orbit look like before the orbits of Uranus, Neptune, Saturn, especially Jupiter, affected the orbit? And that's how you can tell whether or not a comet came around 1,000 years ago, or 10,000 years ago, or 1,000,000 years ago, or has never been close to the sun before. And right now it's looking like this comet may have never been close to the sun before. The problem with that is these objects quite often appear bright when they're far from the sun. They've spent billions of years out at, in a light year or so, half a light year to a light year from the sun. They've basically been in cold freeze, cold storage, have had minimal heating. And so once they get relatively close to the sun, and relatively close could be 40 AU, distance of Pluto, 20 AU, distance of Uranus, 10 AU, distance of Saturn, they have a lot of really volatile ices that are now sublimating and burning off for the first time ever. And so it releases a lot of dust, creates a big coma, and the object looks really bright for an object that's that far out. But then they have a habit of disappointing or even disintegrating when they come closer. And think of many of history's biggest comet fails. 1941, there was a comet called Cunningham. Of course, we all know the name Kohoutek. Some of us may remember Comet Austin, 1989, 1990. And then most recently, Comet Ison, which was also Comet of the Century, and it didn't even survive perihelion. It broke up. And the estimates were that its nucleus might have only been 50 meters across at the time of its breakup. But here is a comet that looks super bright when they discovered it out at the distance of Saturn. So it's possible that A3 may be similar to this. That, again, we've got a comet that is being hyped, and I guess could potentially, just show here, if I take its current brightness and I assume a relatively conservative brightening trend, it would get up to about magnitude 3, maybe a little brighter. Of course, this is when it's very close to the sun, and in some cases when it's only a few degrees from the sun. And then if I correct for the dust forward scattering, it could be 3, 4, 5 magnitudes of enhanced brightness. So you could be talking about a comet that's getting up to magnitude -1. Again, magnitude -1 at 3 degrees from the sun, probably not going to see. But, a comet here that's about 0 at the first magnitude, when it's now pulled 10, 15 degrees from the sun, could be really nice to see there, especially in the evening sky for us. But it's very possible that this is even though I'm using a conservative brightening trend, it may not even be this bright, and it's very possible the comet may even disintegrate before it even gets this far. So this is one we're just going to have to watch and see. But just to kind of explain a little further on its observability, like I mentioned before, we lose track of it kind of in the early summer last year at 10th magnitude. Then it spends a lot of time really too close to the sun to be seen, at least from the northern hemisphere. Southern hemisphere might be able to follow it as it brightens to 3rd, 4th magnitude. We might be able to get peaks of it through astronomical twilight if it does get brighter than about 1st or 0th magnitude. And at the date of perihelion, it'll only be 22 degrees from the sun, but still drawing closer. And then when we really get that massive scattering, it's only 3 degrees from the sun. And yeah, it could be 3rd magnitude, it could be negative 3rd magnitude. We really don't know. And that's why sometimes comets like Comet West in the 70s was a surprise, because of course that one broke up, increased a lot of dust, and then it had this forward scattering, which made the comet a lot brighter than predicted. So it could still surprise us. After it passes very close to the sun, it kind of rockets into the evening sky for us here in the northern hemisphere. So at least a couple of days or a week after that close approach to the sun, if the comet is still a going concern, we should be able to see a nice 2nd, 3rd magnitude object. By then, of course, the phase angle will decrease, so forward scattering won't be quite an issue. One nice thing is only a few days after it's passed close to the sun, so this is after now it's rocketing into the evening sky from the northern hemisphere, we basically cross the orbital plane of the comet. So if this comet is still nice and bright and has released a lot of dust, we should see a nice antitail at this time as well. And the antitail may actually be benefited because even though the comet's head will be at one phase angle, since the antitail is pointing at the sun, it'll actually be at a better phase angle. So in fact, the antitail may actually be brighter than the comet itself, at least the surface brightness, just because it's getting more of this increase with dust forward scattering. But I guess if I'd say anything about Comet 2023 A3, we'll just have to wait and see. Like I said, it could be a complete disappointment like ISON and disintegrate even before it gets to perihelion, and there may be little left of it after perihelion. At the same time, maybe we're looking at another Comet West, something that'll pop out of the sun and be negative 3rd magnitude with an antitail and everything and be impressive. We'll just have to wait and see. That's one reason why comets are so fun to observe. You never do know what you'll get. That's almost exactly an hour. You would think I actually timed these, but I don't.
Here. All right. Bob is back. Our video is back. And we are ready for questions.
Do we have any questions for our presenter?
Two places.
Go ahead.
Will the analysts will be determined if it's going to be in the Haley?
When will we determine if Atlas will be in the Haley family?
Oh, can you repeat the question?
It's when can we determine, or when will we determine if the new Atlas is in the Haley family or Halley family?
This new comet, the A3 comet?
Yeah.
Oh, so this is a long period comet. So the Halley family comets have orbits between about 50 and 200 years. This particular one right now looks like it doesn't really have an orbital period. It's on what we call a hyperbolic orbit, which means it's not bound, even though it was orbiting the sun out at, some good fraction of light year. This particular pass is a hyperbolic pass, which means it's coming in with a little bit too much energy. So it's going to swing around the sun, and the planets aren't helping here because they're adding some perturbations to it. It'll swing around the sun and may never come back. So that happens a lot too, where comets are kind of one and done. They fall into the sun, but then because they're approaching the sun and Jupiter and Saturn tugs on them in just enough in a certain way that then they leave and they never come back. So it's possible this comet doesn't really have an orbital period because it's an open orbit.
Are you familiar with an app called Space Engine?
I'm not.
It's a universe simulator. I used it a lot to show things, but one of the things you can do is turn comet orbits on, and it's got a lot of long period comets. And then if you can zoom you can go anywhere in the universe with it, but if you go about 10 light years away, you can still see the orbits of some of these long period comets that far away. It's amazing.
Yeah, I mean, that's a lot of them can get out to about 1 light year, half a light year to 1 light year, which means there definitely have been times in the solar system's past where stars have gotten close enough to the sun where they've passed through that Oort cloud. And some of the predictions but some of the explanations for some of the major extinction events in the past is that, a star passed through the Oort cloud, shook up these comets, and enough of them got thrown into the inner solar system that the Earth kind of got broadsided by a few.
Yes, go ahead.
How many comets have ever hit the moon or the Earth?
How many comets have hit the moon or the Earth? I don't think that number is even knowable because it's still happening. I mean, you take a look at the surface of the moon; it is completely pockmarked, and that means the Earth was probably the same. Thank you, atmosphere, got hit by the same amount. And you take a look across the solar system, everywhere except Io and Venus, you've got craters. So the early solar system was not a friendly place.
Does it fall like a billion?
Probably, or more.
And the thing is, you can't tell a crater that was created by an asteroid versus comet. You can't tell the difference between the two because they're similar enough in structure. But it also depends on how small do you define a comet or asteroid. I mean, every second of the day, the Earth is getting hit by thousands of asteroids. You call them dust. They're meteors, but you can consider them asteroids, just really, really small asteroids. Yep.
All right. It is approaching 8:30. Let's give our speaker a hand. Thank you very much. Yes. This is your audience. Your audience.
Thank you.
All right. So after the meeting, we're going to be going to. We still have time to go to the Coney Island at Groesbeck and 12 miles, what we did last time. Again, our next open house is June the 24th. Be there or be square. Our next meeting is July 3rd at Cranbrook Institute of Science. And that's it. Good night, everyone. And look up.
Thank you all for joining the Zoom call, and glad at least half of that worked. The rest of it'll work for the Cranbrook meeting.
Good night.
You learn how to stream to YouTube the right way. See you, Jason.